Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Rotational Viscometers Part 2. In the previous lecture, we started discussing about working principles for rotational viscometers. In the rotational viscometers category, we started with concentric cylinder rheometers, right. For that case, we have developed equation for the shear stress calculations, and then we have also developed equation for a shear rate calculation as well. So, we will be having a recapitulation of whatever the things that we have discussed in the previous lecture. When you use the concentric cylinder rheometers for measuring the rheology of a fluid, then the shear stress that you can measure by using the torque, if you know the torque, then you can measure the shear stress easily by Mi by 2 pi Ri square L, where Mi is nothing but torque and then Ri is the radius of the inner cylinder. This equation you can use when you are measuring, when the torque is measured on inner cylinder. Okay. This L is nothing but the height of the cylinder. Okay. So, if the torque is measured on outer cylinder, then shear stress you can calculate by using this equation m naught by 2 pi r naught square L. M naught is nothing but the torque measured on the outer cylinder, and then r naught is nothing but the radius of the outer cylinder, L is nothing but the height of the cylinder, right. So, these concentric cylinders, the annular space whatever is there, that is very narrow. Then what is the shear rate expression? If that gap is very large, then what is the expression for the shear rate? Those things we have seen. For very narrow gaps, that is when Ri by R naught is greater than 0.99, that means almost they are touching to each other, then what we can say? We can say that the curvature effects would be negligible, and then avoiding the curvature effects, we got that shear rate is nothing but omega I R bar divided by R naught minus Ri. R bar is nothing but the midpoint distance between R naught and Ri, that is R naught plus Ri divided by 2. But however, it is always not possible to have such narrow gaps, but majority of the concentric cylinder rheometers commercially are available, they are having K value less than 0.99, right. So, it is not true for all the cases, but majority of them will have K less than 0.99. So, then you cannot say that the curvature effect is negligible and then you start using this equation. This equation you can use only when you say the curvature effect is negligible, that you can see when the gap between outer cylinder and inner cylinder is very, very small, negligible gap is there, right. When the gap is sufficiently large enough, then shear rate expression we obtain as gamma dot as function of tau is equals to 2 tau d omega by d tau. Tau we already obtained either of these expressions. So, tau is known, and then omega rotational velocity, at what rotational velocity the cylinder is rotating, that anyway we know experimentally. So, you know all the quantities in the right hand side. So, then left hand side shear rate you can find out, right. So, it is a generalized one where the K is less than 0.99. Okay. But for a very large gap case, when K is smaller than 0.1, then we obtained this gamma dot Ri, that is nothing but gamma dot at inner cylinder of radius Ri. So, that is gamma dot Ri is approximately equals to 2 omega I d ln omega I by d ln tau Ri. Since tau is directly proportional to torque, this equation can also be written as 2 omega I d ln omega I divided by d ln Mi. This is what we can have. Okay. So, now shear stress equation you are having only say one equation irrespective of the gap. Okay. So, but anyway you do not go for a very large gap in general, but moderate gaps in general you use, right. However, we have developed the equation. So, shear stress is anyway irrespective of the gap we can use any of this equation, but when you wanted to calculate the corresponding shear rate, then you first calculate what is the value of K, and then accordingly you have to choose an equation. So, if gap is very narrow, so then you can use this equation for shear rate. If gap is very large, then you can use the last equation for the shear rate. But sometimes we may have intermediate gap also. So then what expression for shear rate should we use? That is what we are going to see now in this lecture. For fairly narrow gap, that is when 0.5 less than k less than 1, so that is k between 0.5 and 1, then what should we do? So often concentric cylinder rheometers are using such fairly narrow gap. You cannot say very narrow, you cannot say very large, but in between these regions. So then what we have to do, in order to find the shear rate in this case where the gap is fairly narrow, then whatever the equation 18 in the previous lecture that we have derived, we have to apply Maclaurin series for that equation. What is equation number 18? Is nothing but this equation, that is 2 tau Ri d omega I by d tau Ri is equals to gamma dot tau Ri minus gamma dot tau R naught. Recapitulating again, tau Ri suffix Ri is nothing but the shear stress measured on the inner cylinder surface. Tau R naught is nothing but shear stress measured on the surface of the outer cylinder. Okay. So that is the difference. That is the difference, right? Your geometries that we have, like this. Concentric cylindric geometry. So this is Ri. So if you are measuring shear stress on this surface, then we call it tau Ri. If you are measuring shear stress on this surface here, then we call it tau R naught. Okay. Corresponding gamma dots are nothing but gamma dot Ri and gamma dot R naught. That is what we have seen. These are the notations that we are using last class and then this class as well. So now this equation, when you apply the Maclaurin series, this equation number 22 you get for gamma dot tau Ri, or gamma dot Ri is omega I by minus ln k multiplied by 1 minus ln k by n plus ln k by n whole power 2 by 3 minus ln k by n whole power 4 by 45. This is what we have. Now in this equation, omega I is known already to us, right? Omega I is already known through the experimental experimentation. At what rotational velocity are you rotating the inner cylinder, right? K, ratio between radius of inner cylinder and radius of outer cylinder, that is K, that also we know, right? What is N? N is nothing but d ln mi by d ln omega I. Okay. It is nothing but power law index, but in terms of torque and rotational rate, we can write N is equals to d ln mi by d ln omega I. Now this equation, this series goes on. So how many terms should we include? After how many terms we can truncate the series? That is the another important question, right? That depends on the value of minus ln k by n. How much value is it having? So accordingly, we have to take number of terms in the series. Okay. If minus ln k by n is less than 0.2, then first two terms give an error of less than 1%. So you can include only first two terms, that is sufficient. But minus ln k by n is between 0.2 to 1, then third term should also be included in the series at previous equation number 22. And then for k greater than 0.5, if n is constant, over the entire region of tau Ri to tau R naught, then we have the power law case and equation 18 becomes as below. We are not going to simplify this equation, but anyway you can do it anyway straightforward. So gamma dot Ri is nothing but gamma dot function of tau Ri, gamma dot R naught is nothing but gamma dot function of tau R naught. Okay. That is what the notation that we are having. Okay. So gamma dot Ri is nothing but 2 omega I divided by n 1 minus k power 2 by n, and then gamma dot R naught is nothing but minus 2 omega I divided by n 1 minus k power minus 2 by n. So these are the equations for the shear rate. Depending on the gap, which equation should be used, that now we should be very careful, because now anyway we have the knowledge whether it is narrow gap, whether it is large gap, whether it is fairly narrow gap. So then we have the equations for the shear rate. shear stress equation we have already obtained irrespective of the gap. Okay. So, this is what about the concentric cylinder rheometers if you are using to measure the shear stress and shear rate. Okay. Now, we will be discussing about how to measure the normal stress using the concentric cylinders, right. However, before going into those topics, what you have to observe, it is not necessary that always the inner cylinder is rotating. Many a times inner cylinder is fixed and then outer cylinder is rotating. Sometimes it is also possible that both inner and then outer cylinders are rotating at different speeds. Let us say if inner cylinder is fixed and then outer cylinder is rotating, then simply what you have to do, you have to replace omega I with omega naught. Omega naught is nothing but the velocity at which outer cylinder is rotating. Okay. And then you can use these two equations for shear rate. Right. Now, we will be discussing how to measure normal stresses in co-ed flow or concentric cylinder geometry, whatever is there, concentric cylindrical geometry when the narrow gap is there. So, then that geometry, in that geometry when there is a flow, then that flow is often called as a co-ed flow. So, normal stresses in co-ed flow, that is normal stresses in concentric cylinder geometry, that we are going to discuss now. What we have seen that on rotating elastic liquids or viscoelastic liquids, they climb the rotating cylinder, that we already seen when we were discussing about the classification of non-Newtonian fluids. However, if the fluid is Newtonian, then we can see slight depression at the surface, near the surface, that the liquid Newtonian fluid surface becoming slightly depressed, whereas the viscoelastic surface is climbing the rod on rotation. So, that we know, but why this climbing of a rod takes place, that also we have discussed because of the normal stresses. So, can we prove that mathematically now? That is what we are going to see now. Surface, this whatever the liquid surface climbing the rod, that acts as a sensitive manometer for small negative pressure near the rod generated by the centrifugal force on rotating the cylinder. How this rise can occur from the normal stress terms to be understood now. So, now in the previous lecture what we have done, we have done simplification of r, theta and z components of equations of motion in cylindrical coordinates, and then each equation has given some kind of information. One was giving information about the normal stress, or providing a simplified equation to get the normal stresses. One equation providing the simplified equation to get the information about the shear stress. Another equation was relating the hydrostatic pressure and then gravitational force and all those kind of things. So, r component of equation of motion, yesterday we simplified, we got a simplified expression which provide information about the normal stresses. So, that equation I have rewritten here again. In the previous lecture, we have simplified r component of a momentum equation for the case of concentric cylinder. So, this is what we got, this equation we got. Okay. So, now this equation we make use in order to get the information about the normal stresses. So, here sigma is nothing but the sum of p and tau, that now we substitute here. In place of sigma we are substituting tau plus p. So, then we have sigma rr is nothing but tau rr plus p, right, and then sigma theta theta is nothing but tau theta theta plus p. So, this one is there, right, minus dou p by dou r is anyway is there. So, when you differentiate this particular term, then you have tau rr plus r dou tau rr by dou r plus r dou p by dou r plus p, and this term as it is, last term is also as it is. Further, if you bring this r inside of the parenthesis, then you get tau rr by r plus dou tau rr by dou r plus dou p by dou r plus p by r minus tau theta theta by r minus p by r. These two terms are coming from here. So, then what we have, this dou p by dou r, this minus dou p by dou r, this plus p by r, this minus p by r can be cancelled out. So, then finally, we have minus rho v theta square by r in the left hand side remaining as it is, that should be equals to dou tau rr by dou r minus tau theta theta minus tau rr by r. This is what we have. And then this information tau theta theta minus tau rr is nothing but the first normal stress difference. Okay. So, further we can simplify this equation. If the gap between the cylinder is small, then what we can see, whatever this dou tau RR by dou R is there, we can apply Taylor expansion and then we can write this equation as tau RR at Ri minus tau RR at R naught divided by R naught minus Ri. That is what we can simply write without any difficulty. So, from this equation 26, after striking off the inertial term, then we can have tau theta theta minus tau RR is equals to R dou tau RR by dou R, and then from equation 26b we have dou tau RR by dou R is equals to tau RR at Ri minus tau RR at R naught divided by R naught minus Ri. This is what we have. So, now in place of dou tau RR by dou R, we will be writing this expression, and then in place of R we have to select the position at which we are measuring the normal stress. So, then this R, usually we take R bar, that is midpoint between Ri and then R naught. So, first normal stress difference tau theta theta minus tau RR you can find out from this expression easily without any difficulty. Okay. Tau RR at Ri minus tau RR at R naught is simply the pressure difference between the inner and outer cylinders, and then we have already seen that first normal stress difference can be largely positive number when we have taken an example of viscoelastic fluids. So, then due to this, pressure on inner cylinder will be higher, causing the fluid to rise up the rod. That is the reason, the rising of the viscoelastic fluid along the rotating rod, rotating cylinder in this case, is taking place because of this normal stress differences. Okay. So, this is all about how to measure the normal stress differences, shear stress, shear rate, etc., using the concentric cylinder rheometers. Now, there are some issues with respect to the accuracy of these equations because of the several other issues like end effects, slip effects, etc., as we have seen in the capillary viscometer also. Some of them that one should be worried in the case of concentric cylinders are what is this first normal stress difference, how much it is, then rod climbing effect, then end effect, then secondary flows because of Taylor instabilities, and then shear heating in coed flow, etc. These are some issues one can think of, but however, we are not going into the details of all of these topics because we are we supposed to concentrate on the applied rheology. So, since we are talking about applied rheology, some basics are required. So, then that is what we are discussing. We do not need to go into the details of all these things anyway. So, now we take an example problem. Following steady shear data for a salad dressing has been obtained at 295 Kelvin using a concentric cylinder viscometer, Ri 20.04 mm, R naught 73 mm, L 60 mm. Obtain the true shear stress versus shear rate data for this fluid. What is the data is given? Data is given, this omega in radians per second is given, and then torque in Newton meters it is given. Okay. So, if omega is given, torque is given, so then you can find out the shear rate, shear stress respectively. So, torque you can use to get the shear stress expression, omega you can use to get the shear rate expression, but in order to get the shear rate expression we have to be specifically clear about what is the value of K, then only we can select the corresponding equation for shear rate. So, what we see Ri by R naught in this case 20.04 by 73, that is 0.275, that is very much smaller than 0.99. So, then we cannot say that the curvature effect is negligible, but it is more than the 0.1. So, then we cannot say that the gap is very large. So, then what we have to do? We have to take a case where fairly narrow gap equations are provided, right. So, that is sample calculations. Shear stress tau Ri is equals to m by 2 pi L Ri square, this we know. First data point m is given as 6.09 into 10 power minus 4 Newton meters, 2 pi L is 60 mm, Ri is 20.04 mm. So, when you substitute these numbers and then do the simplification, you get tau Ri 4.025 pascals. So, for this k value of 0.275, appropriate equation of shear rate is 2 omega multiplied by d ln omega by d ln tau Ri. That means, for each mi value, what is the corresponding tau Ri value we have to calculate, as we have calculated for the first point. Omega corresponding to that one, what is the omega value is already given. So, then omega versus tau Ri data, whatever is there, that you have to plot on a log scale and then get the slope of that curve. So, that comes out to be 2.73. When you plot ln omega versus ln tau, you get a straight line like this, and then when you get the slope of this one, you will get it as 2.73. So, first point, gamma dot Ri is nothing but 2 omega d ln omega by d ln tau Ri is equals to 2 multiplied by omega, first data point omega is 0.146, and then d ln omega by d ln tau Ri is nothing but 2.73. So, gamma dot Ri 0.8 second inverse for the first data point. Likewise, we have to do for all the data points, then you have tau versus gamma dot information. That information is provided here in the tabular format. Okay. So, now when you plot it, what you can realize that this material is slightly viscoplastic, because the tau naught is there, but it is very small value, approximately 3 pascals or something like that, okay, 4 pascals or something like that. And then this n value is coming out to be 0.3661. So, it is a Herschel-Berkeley fluid with a mild yield stress value. Okay. So, now we have done an example problem also, how to use the equations of a concentric cylinders rheometer to obtain the rheological behavior of any given fluid, if you know the omega versus the rotational velocity versus torque information from the experimental data. Okay. Now, we take another geometry, cone and plate rheometer. Okay. So, perhaps this is the first geometry used to obtain the normal stress differences for viscoelastic fluids, and then that has been reported by Mooney and then Ewart in 1934. But however, this work extensively carried forward by Russell to measure the normal stresses, and then because of work by Russell, the present Weissenberg rheogonometry, Ferrani-Shirley instruments, etc. have been developed. That is purely because of the Russell's work. Okay. So, in the current scenario, cone and plate rheometer is the best option if you wanted to know the rheological behavior of non-Newtonian fluids. Why? Because one reason is the constant shear rate. In this geometry, you can maintain the shear rate constant, and then direct measurement of first normal stress difference by a total thrust. So, because of these two reasons, so this is the best rheometer for studying the rheology of non-Newtonian fluids. So, now that we are going to see how to develop the equations. So, like in the concentric cylinder case, we developed the equation for shear stress as function of torque, and then shear rate as function of rotational velocity, normal stresses as function of the pressure differences, etc. All those things we have seen. How we got those information? We got those information by simplifying the momentum equations. So, same thing here also we are going to do. We are going to simplify the equations of motion and then try to get the simplified equations for a cone and plate geometry of a certain constraints. So, what are those constraints, what are the how the geometry looks like, that is what we are going to see now. So, now since it is a cone and plate geometry, so there is a plate and then there is a cone kind of arrangement is there, something like that. Okay. So, now here the plate is having this plate is here, right. The radius of this plate is r. Now a cone is placed on this geometry something like this. Okay, so this is your cone, right? The cone angle is beta. Okay. Now what we have to realize, so let us say this is the cone, you are putting like this upside down like this, right. So now I am just putting the up like this to have a kind of clarity. So now this direction it is rotating, that direction of rotation whatever is there, that is phi direction, right, and then theta direction is in this direction. Okay. So this position in this position is the radial direction. Okay. So now the rotation is in the phi direction, rotating it, the cone is rotating in the phi direction at a velocity omega, right. Theta is measured from the top, so we can see the arrow here. So this arrow indicates that theta is measured from this top like this. Cone angle is only beta, small, very small cone angle we in general use, right. So now this direction is your r direction. Okay. So once it is clear, so then whatever the fluid is there, that is being confined in between this cone and plate, right. When the cone is rotating, deformation in the fluid will take place because of the rotation of the cone. Okay. So now once there is a deformation, so the corresponding shear rate, corresponding shear stress we have to measure. Okay. Since here the cone angle, whatever this cone angle is there, that is very small. In general, the cone angle is taken very small, so that the whatever the shear rate etc. is there, so that can be maintained constant. Okay. So now here the cone angle that is taken very small in general for most of the cone and plate geometry, because the purpose is that when the beta cone angle is very small, so for one thing is that you can avoid the curvature effect, and another thing that the shear rate can be maintained constant. Okay. So the gap is narrow, so then we can say that shear rate almost remains constant. So that is the advantage. So assumptions here, flow is rotating in phi direction. So the only velocity component is existing in phi direction, so that is V phi is there. So this phi now function of r and theta, because this fluid is whatever is there, that is because of the rotations is moving towards the r direction, as well as it is moving towards the theta direction also because of the cone shape. Okay. So we cannot say that V phi is function of r only, it is also function of theta. Okay. So and then, but however compared to V phi, Vr V theta are 0. Then flow is steady, laminar and isothermal, negligible body forces, and then beta cone angle is very small, 0.1 radians, that is approximately 6 degrees or less. So such small cone angles in general used in order to maintain the constant shear rate. Then spherical liquid boundary is there, because the cone is can be best represented by the spherical coordinates, and then symmetry in phi direction. So dou by dou phi I of anything is 0. Okay. So these are the constraints. So now using these constraints, we are going to simplify r, theta, phi components of equations of motion, so that we get some simplified equations, which we can use to get the information about shear stress, shear rate, and then normal stress differences, etc. So let us start with r component. So r component of equation of motion in spherical coordinates, this is what we are having. So now this equation we are going to apply the constraints that we have seen in the previous slide. So it is a steady flow. So first term is 0, Vr is 0, V theta is 0, V phi is not 0, but dou by dou phi of anything is 0 because of the symmetry. V theta is 0 and it is remaining here. Pressure we do not know as of now. Normal stress components tau rr we are not separating, we are not removing, because we we are trying to develop equations which can also be used for the viscoelastic fluids. Okay. So, shear stress, which component is existing in this slide. So, previous slide, the rotation in phi direction is there. So, then only tau theta phi component of shear stress is only existing, other component of shear stress are not existing. Okay. So, that is the constraint. So, then because of that one, this is anyway 0. So, because of symmetry this term is 0. Okay. So, this we cannot cancel out, this we cannot cancel out, and then we are not taking any gravity forces. So, then this equation we are having simplified equation. Okay. So, this term and this term in the right hand side, only minus rho v phi square by r on the left hand side, these terms are remaining. So, now in the case of inertia, in such kind of cone and plate geometries, usually rotational speed are not very high that you need to convert, that you need to worry about the inertial forces, etc. But however, if there is higher speed, so then these all terms should be included. So, let us say if we have the case where the inertial forces are inertial terms and then pressure terms are independent of radial coordinates, then we can have this final equation. Okay. So, this is the equation we can use in order to get information about the normal stress differences. Then theta component of equation of motion is this one in spherical coordinates. So, now we apply the constraints. So, first term is 0 because steady state, Vr is 0, V theta is 0, V theta is 0, Vr, V theta both are 0, this is not 0. So, this term would be there. Pressure we do not know anything, this shear stress term is not there. So, extra stress components we cannot cancel out, because of symmetry this term is 0, and these two terms are identically equal to each other at least for a laminar flow conditions. So, we can strike out that term because the difference is 0, but this term we cannot strike out because of this one we have to worry about extra stress component. And then body forces we are not taking, so this is 0. So, then what we have, this equation we are having right hand side 3 terms, left hand side 1 term it is there. Okay. In the absence of inertia in theta direction and then pressure independent of theta direction. So, then this equation we can write like this. So, from here also we get some information about the normal stresses. Okay. That is the reason cone and plate geometry is the best option if you wanted to find out normal stress differences for an viscoelastic fluid. So, phi component, so this is the equation. Now, applying the constraints of the problem. So, this is steady state. So, 0. So, Vr is 0 because of symmetry this term is 0, V theta is 0, Vr is 0, V theta is 0. So, left hand side we do not have any terms, and then because of symmetry this term is 0. So, this component of shear stress is not existing, this component of shear stress is existing. Because of symmetry this term is 0, these two are equal to each other. So, then the difference is 0, and then this component of shear stress is existing. So, we cannot cancel out. Body forces we are not taking into the account. So, then we have this equation, simplified equation. Further you do the differentiation and simplify. So, then you get this equation 1 by r dou by dou theta of tau theta phi plus 3 cot theta by r tau theta phi is equals to 0. So, now this equation will give us some information about shear stress. Okay. So, now boundary conditions at the wall or periphery of bottom plate. So, what we have? We have a bottom plate like this. Within this one we have a cone like this, arranged like this, right, something like this. So, now in this case what we have taken? We have taken the bottom plate, whatever this is there, that is stationary, right. So, obviously V phi should be 0, and then angle, you know, how are we measuring theta? So, this is the theta direction, theta we are measuring from top. So, theta is equals to 0 is this one, and then this line is nothing but theta is equals to pi by 2. So, at theta is equals to pi by 2, V phi is equals to 0, because bottom plate is stationary. But at lower edge of the cone, at this cone, the velocity is not 0, because the cone is rotating with certain velocity, right. So, that is at theta is equals to pi by 2 minus beta, because this cone angle is beta, this entire is pi by 2. So, pi by 2 minus beta is the location, nothing but the lower edge of the cone. So, cone lower edge is rotating with omega. So, at theta is equals to pi by 2 minus beta, we have omega r sin pi by 2 minus beta as a kind of velocity component, because the cone angle beta is very small. So, then you can get this value anyway. So, V phi at theta is equals to pi by 2 minus beta, it is not multiplied, but it is at theta is equals to pi by 2 minus beta. So, that you get this information. We have started with like V phi is function of r and theta, right. So, now you can see r component is there, and then this is pi by 2 minus beta is nothing but theta. So, it is function of both r and theta. Okay. So, however, when beta is very small, sin pi by 2 minus beta, you can write it as cos beta. When you expand it, you will get 1 minus beta square by 2 factorial plus beta power 4 by 4 factorial and so on. So, that you can write is approximately equals to 1 if beta is very small. So, that means sin pi by 2 minus beta is approximately equals to 1 if beta is small. So, then we can write V phi at theta is equals to pi by 2 minus beta is nothing but omega r. So, the velocity boundary conditions for the velocity we got. Now, we see shear stress information how to get. So, equation number 3, this is what the equation number 3, that is when we simplified the phi component of equation of motion in spherical coordinates, then we got this equation just a couple of slides before, that is equation number 3. So, now this equation, if you do the integration, you will get C1 by sin square theta, right. So, now this equation can be useful only when you get the C1 information, that we can get from the experiments if you know the torque. If you know the torque, from the torque balance, torque m is equals to integral 0 to 2 pi 0 to r square tau theta phi at pi by 2, that is at what location are you measuring, dr d phi is equals to 2 pi r cube. Now, integration after you do 2 pi r cube by 3. So, 0 to r limits if you substitute, you know, you will be having 0 to r cube by 3 minus 0 cube by 3. So, that is 2 pi r cube by 3 tau theta phi at pi by 2. This we do not know, still we do not know, but we can make use of this equation to get that expression. So, from equation 7, tau theta phi at pi by 2 is nothing but C1, because sin pi by 2 is nothing but it is 1. So, sin square pi by 2 would be 1. So, tau theta phi at theta is equals to pi by 2 is nothing but C1. So, that means tau theta phi is equals to tau theta phi at pi by 2 divided by sin square theta, or tau theta phi at theta is equals to pi by 2 is nothing but tau theta phi sin square theta. So, this you can use in this equation number 8, so that you get tau theta phi as function of theta is equals to 3m by 2 pi r cube sin square theta, right. After substituting this one in equation number 8, we have written only tau theta phi as function of theta one side, and rest all other terms we have taken to the other side. So, then we get 3m by 2 pi r cube sin square theta. Now, again beta is very small in general, very small cone angle. So, sin square theta at pi by 2 minus beta. Now, theta is nothing but at what location are you measuring the shear stress, that is the reason, that is important. So, you are measuring at this location, at the lower edge of the cone. At the lower edge of the cone, at this location you are measuring tau and gamma dot also, of course, that we are going to do. So, this location is nothing but theta is equals to pi by 2 minus beta. So, in this equation, if you substitute theta is equals to pi by 2 minus beta, so then whatever the equation that you will get, that is nothing but 3m by 2 pi r cube is the expression for shear stress. So, shear stress expression we already got for the case of a cone and plate geometry. Okay. Now, we try to get expression for shear strain rate. So, tau theta phi is nearly constant for small cone angle that we have seen. So, then obviously shear strain and shear rate will also be constant nearly, because that beta is very small, less than or equals to 6 degrees in general. Okay. And then that is how that only that much or even smaller beta angle cone and plate rheometers are manufactured in general. Okay. So, what we have, shear strain gamma, that rotation in the phi direction and then variation is in the theta direction. So, then what we have, d phi by d theta is equals to phi by beta, because of very small angle and then small displacement as well. So, from the components of rate of deformation, we know that gamma dot is nothing but modulus of 2 epsilon phi theta. So, this from the transport phenomena book, this quantity, modulus quantity, that we know that it is sin theta by r, dou by dou theta, v phi by sin theta. Any transport phenomena book, you can see the extra stress component for non-Newtonian fluid. So, then you can get this component. When you expand this one, so then you will get this equation. So, now what you have to have in order to get the shear rate expression, you need to know V phi, then only you can get it. So, that we have already seen, but once again we see. So, now theta at pi by 2 minus beta only we wanted to know the rheology of the material, because we wanted to know the shear rate and then shear stress at the lower edge of cone, which is nothing but theta is equals to pi by 2 minus beta location at this lower edge of the cone, right. So, at theta is equals to pi by 2 minus beta, cot theta is nothing but tan beta, and then for small beta, tan beta is nothing but beta plus beta cube by 3 and so that series goes on. So, then we need only for small beta. So, then we can just write it as it is. Best approximation for velocity profile should be this one, that is V phi is equals to omega r multiplied by pi by 2 minus theta by beta, which are same. So, then approximately it gives a linear profile with respect to r, almost linear profile with respect to r, and then theta components have been also been brought into the picture. So, now this expression you write here in place of cot theta you write tan beta here, and then in place of tan beta you write whatever this expression. So, let us do the simplification. Gamma dot would be 1 by r dou by dou theta of omega r pi by 2 minus theta by beta minus omega r pi by 2 minus theta by beta multiplied by beta plus beta cube by 3 and then modulus. So, this you further do the simplification and then you get this expression omega by beta multiplied by 1 plus beta square plus beta power 4 by 3. So, which approximately you can write beta by, which approximately you can write it as omega by beta, because beta is very small. So, beta square beta power 4 terms would be negligible. So, now we got shear rate expression also, gamma dot is equals to omega by beta, whereas shear stress expression we got it as 3m by 2 pi r cube. So, shear stress and then shear rate expressions we already got by using cone and plate rheometers. By using cone and plate geometry, shear stress and shear rate expressions are these things, which we can use in order to get the rheology of the material. So, now we discuss something about normal stresses, how to measure them. From equation number 1, that is R component of equation of motion, after simplifying, this is what we got, this, right, 1 by r square dou by dou r square tau r minus tau theta theta plus tau phi by r is equals to 0. So, now when you do the differentiation of this term, then you get 2r tau r plus r square dou tau r by dou r, and then this term is as it is. So, now when you bring 1 by r square within inside the parenthesis, then you get 2 by r tau r plus dou tau r by dou r, and then whatever this quantity that we are taking to the right hand side. So, then tau theta theta plus tau phi by r. So, this equation how we write only r dou tau r by dou r one side by multiplying this equation both sides by r. Then what we have, right hand side tau theta theta plus tau phi you will be having, left hand side you will be having 2 tau r. So, that will bring it to the right hand side. So, then minus 2 tau r. So, this expression, this is nothing but n1 plus 2 n2, where n1 is tau theta theta minus tau phi and then n2 is tau phi minus tau r. Okay. Here n2 is steady shear material function and only depends on shear rate, and since shear rate is independent of radial position, so this will also be independent of radial position. N2 will also be independent of radial position. That means dou n2 by dou r should be 0. So, dou by dou r of tau phi minus dou by dou r of tau r should also be 0. That means we have dou tau phi by dou r is equals to dou tau r by dou r. So, now equation 14, this is what we have. Okay. Equation 14 is r dou tau r by dou r. So, in place of r dou tau r by dou r, we can write r dou tau phi by dou r we can write. So, when we write that one, we get equation 14 like this. Right hand side n1 plus 2 n2 is as it is. So, that here now we can write here dou tau phi by dou ln r is equals to n1 plus 2 n2 we can write. So, this is just a pressure measured by a transducer on the plate or on the cone surface. So, for fixed omega, plots of tau phi versus ln r should be straight line. So, obviously that means at a rim of plate, that is at r is equals to capital R, tau phi at r is equals to capital R should have a positive pressure, small positive pressure should be there. Okay. If we assume that stress in radial direction at the rim is balanced by ambient pressure Pa, then tau phi at r is the second normal stress difference, and then that we can get using this equation. It is simpler to measure total thrust on plate. Thus, by making a force balance on the plate, we can have a force due to the thrust f of z is equals to this one, Pa is the ambient pressure. So, now by integrating this equation above equation by parts and then applying this results whatever that we got in a previous slide, and then obviously we know that n1 plus 2 n2 is function of shear rate, and then it is independent of radial position because shear rate is almost constant, that is what we have seen. So, then this quantity n1 plus 2 n2 should also be constant as at least irrespective of the radial position. So, then when you apply that one and then do the simplification, this is what you get the expression for the thrust. Okay. So, if boundary of spherical shape and if surface tension effects are negligible, so then this quantity must be replaced by Pa. So, then we have f of z is nothing but pi r square n1 by 2. So, that directly first normal stress difference can be obtained by the thrust, which you can measure by experimentally without any difficulty. Okay. R n1 is equals to 2 fz divided by pi r square. So, that is about how to measure the normal stress differences, shear rate and then shear stress using cone and plate geometry. Okay. Now, we take an example problem before winding up this lecture. So, a 25 mm radius cone plate, beta 1 degree 18 minutes 45 seconds is used to obtain the following steady shear data for a food product at 295 Kelvin. Obtain shear stress versus shear rate data for this substance, and then the given information is that rotational velocity and then torque is given. Okay. So, solution, cone angle is less than 6 degrees. Okay. So, which is approximately 0.02 radians, whatever it is given. So, then what we can do, we can, for the first data point, tau theta phi is nothing but 3 m by 2 pi r cube. M for the first data point is 1.34 into 10 power minus 4 Newton meters, and then r is nothing but 25 mm. So, then we get 4.1 pascals. Similarly, shear rate omega by beta, because beta is very small. So, first data points omega is nothing but 2 into 10 power minus 3, and then beta is nothing but 0.02 radian. So, then gamma dot you get 0.1 second inverse. So, likewise for all the data points you obtain shear rate and then shear stress, then you tabulate them like this here. So, then you get shear stress versus shear rate curve like this. Herschel-Bulkley fluid nature with a small yield stress, that is what you can get. So, that is what, how to get rheological behavior of a unknown fluid by using cone and plate geometry, right. We have seen the equations for shear stress, shear rate and then normal stress as well, but we have done this when beta cone angle is very small, then you can maintain the constant shear rate. That is the advantage of this geometry. Another advantage of this geometry is that you can directly measure the first normal stress difference by thrust. Thrust you can directly get from the experimental calculation. So, then N1 is equals to 2 Fz by pi r cube, that you can use to get the first normal stress difference. So, that is the reason the cone and plate geometries are found to be very much useful to study the non-Newtonian behavior, to study the rheological behavior of unknown fluids which are expected to have non-Newtonian behavior. Okay. So, the references for this lecture are given here. So, most of the slides were prepared from this book, Rheology Principles, Measurements and Application by MacAskill. Some example problems have been taken from this reference book by Chabra and Richardson. Other reference books may also provide useful insights about these topics. Thank you.